Okay, hello everyone. Hello, who all are there? All of you have joined. Okay, Sanjana, Ritvik, Visist, Purvik, Kushal. Okay, so today, like as I said yesterday, Shruti is also there. Sai Mihir, hi. As I said yesterday, today we are going to start our revision classes for this JEE mains, and today we are going to discuss chemical equilibrium. Equilibrium. Okay. See, actually, you all have done this chapter once. Okay. So we will not go into that detail. Okay, like every derivation and all, we will not see. Okay. If you have any specific doubt, then you can ask me. You can stop and you can text me over this like portal. You can ask me any specific doubt if you have. Okay. But I'll give you a brief, a brief introduction of this chapter, brief formulas. I'll give you what all formulas are important and the important point that we have here, right? Okay, so and then we'll mainly focus on problem solving. Okay, we'll try to understand the concept with questions itself. Okay, because since we don't have that much time, right? So with problem only we'll try to understand the concept mainly. Okay, so like you see in this chapter, the most important the portion we have, that is Lee Chatlier's principle. Okay, you will definitely have one questions, like if you see any previous year paper, uh, Lee Chatlier principle, based on this you definitely have one, you will definitely have one questions. All other questions related to KC, KP and all that you can do easily, it is not that much stuff. Okay, so basically this chapter is a bit easier, okay, than the other chapter. Okay, it's a bit easier chapter basically. So okay, so I think all of you have joined. Sharanya, Shweta, Rushali, Sriram, Saundarya. Okay, so let's start with this chapter. So, what is an equilibrium? Equilibrium is what? When, like in physics, also we define equilibrium when the forces are balanced. Like, no, when all the forces acting on a particular object, if it is balanced, net force is zero, then the object is said to be in equilibrium, right? So that is also one of the definition of equilibrium. But since this is chemistry and we are dealing with chemical equilibrium, chemical reactions into it, so we have to understand how do we define equilibrium in any chemical reaction. So first of all, when we talk about equilibrium, for equilibrium we required two opposite processes, right? For equilibrium we require two opposite processes, right? Two more important things we have over here, that whether it is given in the question or not, you have to keep this in mind, that equilibrium is only possible whenever the process is going in a closed vessel. If it is open, then the equilibrium will never maintained, right? Like I've told this thing in the class also, the vessel must be closed wherever the reaction is taking place. It must be a closed vessel, then only equilibrium possible, because we have to conserve the amount or the mass of the reactant that we are taking. Because when reactant converts into product, and some of the mass, if it is open vessel, it is going into the atmosphere, then the possibility of equilibrium will not be there, right? The two things. So basically, like in so like we say, when we talk about the direction or direction in which the reaction may proceed, there are basically two types of reaction, right? Two types of reaction we have. There are various other classification of reactions. We are talking about only in terms of direction we are talking about, right? So two types of reactions we have. One is irreversible reaction, irreversible, and the second one is reversible reaction. Irreversible reaction, always goes into one direction from left to right, reactant to product. Okay, reversible may go in both direction, like left to right or right to left. Also means in into the forward direction and backward direction on this. Also, it's possible, right? So in this chapter, we are mainly discussing, or we will discuss about only reversible reaction, because equilibrium is only possible in case of reversible reaction. If the reaction is irreversible, unidirectional, in only one direction the reaction is going on, then the possibility of equilibrium will not be there. Okay, so first thing is this, in this we are dealing with reversible reaction. Okay, and the condition of equilibrium is what? Rate of forward reaction, rate of forward, I hope you all know these things, right? Rate of forward reaction is equals to rate of backward reaction. Rate of backward reaction. Okay, so I'll go a bit fast over here. Backward reaction, rate of forward reaction is equals to rate of backward reaction, then only the equilibrium will be maintained. One thing you must keep in mind, at equilibrium, if you feel any point important, you may write it down. Okay, at equilibrium the reaction never stops, right? If the equilibrium has been achieved, it does not mean that the reaction is not going on. Okay, it is going on, but with equal rate. Okay, the rate at which it is going into the forward direction, with the same rate it is coming into the backward direction, it is going the backward direction only, right? So reaction never stops at equilibrium. Okay, so the next thing here, that is, suppose there is one law over here, that is let me take one reaction. Suppose A plus B gives C plus D, right? So for this, a law we have, that is law of mass action. Mass action, and this suggests that the equilibrium constant Kc is equals to the concentration of product divided by the concentration of reactant. This is equilibrium constant Kc. This we call it as law of mass action. Okay, if any coefficient is there, suppose randomly if I put any coefficient over here, suppose if I write here 2, 3, 4, 5, then we should write here c to the power 4, d to the power 5, a to the power 2, b to the power 3, right? Like this we write. Okay, so this we call it as law of mass action. Okay, um, it says that the equilibrium concentration is equals to the concentration of product divided by the concentration of reactant. And one more thing over here is what, that we know the relation of pressure and concentration, P is equals to CRT. So this concentration term over here, if it is divided by RT, C is equals to concentration term, if it is multiplied by RT, you see it converts into pressure, correct? So when we multiplied here by RT, RT, RT and RT, we can multiply it in the numerator and denominator. So this concentration term converts into pressure, right? So when we write down the pressure over here, then the equilibrium constant there we call it as Kp. It is the partial pressure of product. Let me write down like this only, partial pressure of product divided by the partial pressure of reactant. Okay, so when you take pressure over here, this term becomes Kp. When you write concentration, this term becomes Kc. One relation we have of Kp and Kc, Kp is equals to Kc RT to the power del n. This del n is what? This del n um, is the difference of the number of product and reactant. Okay, number of product and reactant. Del n, with the help of reaction, we can easily find out, right? So if this del n is equals to 0, then Kp is equals to Kc. Greater than 1, then Kp is greater than Kc. Sorry, greater than 0, then it is greater than Kc. Let me write down here. If del n is equals to 0, Kp is equals to Kc, we have del n greater than 0, it is Kp greater than Kc. Del n less than 0, Kp is less than Kc. Right? So these are the three important. From this also they ask question. Okay, this relation also they ask question onto this. Okay. Now the next thing here, it is what, like the which is important. Okay, some basic thing we have discussed. Right. Now see, one thing, let me tell you, it's a question in the question form I'm giving you this thing. Suppose I have one reaction, right? And that reaction is A gives B, right? Its equilibrium constant is given, that is K1. And the another reaction we have that is suppose C gives D, right? K2. This data is given, the first two reaction. You have to find out the equilibrium constant of this reaction. Um A plus B gives C plus D. You have to find out K for this reaction in terms of K1 and K2. First question is this. Second question is A plus C gives B plus D. What is the value of K in terms of K1 and K2? Tell me the value. Yes, anyone? K1 into K2 for the second part. Okay. K1 by K2 and K1 into K2. Yeah, it's correct. You see, actually, how do we get this reaction from the given reaction? That's the question first. Okay. So first of all, you see, uh, this two reaction we have, if we subtract these two, right? If you subtract these two reaction, we'll get what? A minus C gives B minus D. Correct? Right? Or if I add these two, it becomes, okay, let me add this first. A plus B, A plus C gives B plus D. Right? In this, I have made one mistake. This is not possible actually. I'll check this. I'll tell you this. What is wrong? I should write down D over here. We'll tell you. Wait. See, actually, what happens when we add these two? First of all, from this relation, K1 is equals to what we can write? Concentration of B by concentration of A. And from the second reaction, K2 is equals to what? concentration of D divided by concentration of C, product by reactant. And for this reaction, equilibrium concentration in constant K is equals to what? Concentration of B into concentration of D divided by concentration of A into concentration of C, right? Now you see this B by A is what? B by A is K1 and D by C is K2. So K is equals to what? K1 into K2. This is the relation we have for K1 and K2. So one thing that you have to keep in mind, whenever we add two reactions, right? Whenever we add two reactions, so the equilibrium constant of the individual reactions should be multiplied, right? So K1 into K2 will be the equilibrium constant of this reaction, right? Now here I made one mistake. I should write down D over here and B here. Then it is fine. Okay. Then you see A plus D we have to add, right? So A plus D, now when we subtract the first two equation which is given, okay, make the correction over here. It should be A plus D and C plus B. Now when we subtract these two, we get what? A minus C gives B minus D, right? Which further we can write A minus A plus D gives B plus C. Now for this, if I write down the value of K, that will be concentration of B, concentration of C divided by concentration of A and concentration of D. Again, you see B by A is K1, right? D by C is K2. So C by D is what? 1 by K2. So K1 by K2. So when we subtract two reactions, the equilibrium constant of the individual reactions will get divided like this. We'll take the ratio of 2. Yeah. Now you see one more thing here. See, this reaction we are subtracting here, we get this. One more thing we can do, if we reverse, because we have to find out, we have to write down A plus D, right here. So what we do, we just reverse the second reaction. D gives C if you write. So D gives C if you write. So we already have A gives B. It is K1. And when we reverse the second one, it becomes what? D gives C, right? But when you reverse this, so this should be what? This should be 1 by K2. The equilibrium constant also get reversed. Now when you add these two, you'll get the same reaction, which is this. And when we add these two, we know from this one that when we add the two reactions, the equilibrium constants get multiplied. So K1 into 1 by K2 is nothing but K1 by K2. Right? Now to sum up this discussion, whenever we are adding two or more than two reactions, the equilibrium constant of the final reaction will be the multiple of the equilibrium constant of individual reactions, which we are multiplying, which we are adding, right? Second point is what? When we are subtracting, the equilibrium constant of the final reaction will be the ratio of the equilibrium constant of individual reaction. Okay, the reaction which we are subtracting, which is in the minus, for that the equilibrium constant comes into the denominator. Third thing, when we reverse a reaction, the equilibrium constant will also get reversed. So K2 becomes 1 by K2 over here, right? So this is two, three important points we have, which helps a lot in solving the question. Now, on the basis of this only, one question I'll give you. Okay, you see this one. And the question is 2A plus 2B gives D. And one more real equation we have, A plus B gives C. For the first one, equilibrium constant is K1. For this, it is K2. You have to find out the equilibrium constant of the reaction A plus B plus C gives D. This K is equals to what? K1 by K2. How many of you are getting K1 by K2? Pratik is getting K1 by K2. Visisht, Ritvik, Kushal. Okay, everyone is getting K1 by K2. So basically, when we subtract these two, 2A minus A becomes A, 2B minus B becomes B, and this side becomes D minus C, and that's C I have written this side, right? So the equation or the relation here will be K1 by K2, right? The simple one. Okay. Now you see the next thing that we'll discuss is degree of dissociation. Degree of dissociation, which is represented by alpha. Okay. So it is what? It is the number of moles. Alpha is equals to the number of moles dissociated divided by total number of moles initially taken. Initially taken. Okay, so basically degree of dissociation out of 1 mole, how many moles has been dissociated? That is what you have to find out. Okay, this I think you should know. You know all these things, right? There are a few formulas for this degree of dissociation we have, right? One formula, when the vapor density is given, right? When the vapor density is given, so when vapor density is given, if vapor density is given, then alpha can be calculated by, it is capital D minus small d divided by n minus 1 into small d. Okay, here you have to keep this in mind that this d, capital D, is the vapor density when there is no dissociation, or this is the actual vapor density when there is no dissociation. This data will be given. Small d is observed vapor density. All these value will be given in the question. All you have to do is what? You have to keep this formula in mind. Okay, observed vapor density. Okay, this n is important. You must keep this in mind. What is n? It is the total number of product. Total number of product. Okay, only product we see, nothing to do with reactant over here. Okay, total number of product. So this is one formula. Now vapor density and molar mass also has relation. We know molar mass is equals to what? Molar mass is equals to 2 into vapor density, correct? So this formula we can also write down in terms of molar mass, right? So the second formula will be alpha is equals to molar mass minus small m divided by n minus 1 into small m. Again, small m is what? Observed molar mass, and m is what? The molar mass or the given molar mass when there is no dissociation. Okay, just d is equals to, or molar mass equals to what we'll write? 2 into vapor density, right? Multiply by 2 here, 2d minus 2d and 2d here also. This 2D becomes m, small m, small m. That is what the formula we have. One more formula which is not that much important. Okay, this formula, there are few questions that you may see. Okay, one more formula we have when, excuse me, when temperature and pressure is given. Okay, when temperature and pressure is given, right? So alpha is equals to, we write T1 P2 minus T2 P1 divided by T2 P1. This is the formula. This formula is not that much important, but yeah, we have one formula in terms of temperature and pressure that we have to keep in mind. Okay. Okay. Reaction quotient concept, I think you know already, right? So that I am not discussing. If you have doubt, you ask me, then I'll discuss. Otherwise, let it be. Reaction quotient concept. Okay. When Q is equals to Kc, the reaction is at equilibrium. When Q is greater than Kc, then backward reaction favored. Q less than Kc, forward reaction favored. Yesterday also I have discussed this one of the class, right? This in the class, right? One relation we have of equilibrium K is equals to A e to the power minus del H by RT, right? This only suggests that K depends on equilibrium constant depends upon temperature, right? And when we take log and we derive the relation at two different temperature, so log of K2 by K1 is equals to minus del H divided by 2.303 R 1 by T2 minus 1 by T1. Okay. Now you see, if the reaction is exothermic, del H is less than 0, right? So when del H is less than 0, as T increases, so T2 greater than T1 when T increases, correct? So 1 by T2 less than 1 by T1 and 1 by T2 minus 1 by T1 is less than 0. This term is negative. This negative becomes positive. Del H is already negative. So K2 is less than K1 we are getting here. Right? This is only the one I am discussing here. Rest you can understand. Okay. K2 is less than K1, right? So what we can say in this, that in exothermic reaction, as temperature increases, equilibrium constant decreases and backward reaction will be favored, right? Whenever K is increasing, the reaction has tendency to go into the forward direction. If K is decreasing, then backward reaction will be favored, right? So what we can say, exothermic reaction, as temperature increases, backward reaction will be favored since K is decreasing. Reverse of this, when the K is decreasing, then we'll get K2 is greater than K1, so forward reaction will be favored. Similarly, you can understand for endothermic reaction, there will have del H greater than 0. Again, two case you can analyze into this, what uh, will be the relation of K1 and K2 that you can understand. Okay. Now we have one more relation of del G and equilibrium constant, right? One relation we have del G, that is change in Gibbs free energy, is equals to del G naught plus 2.303 RT log Q, reaction quotient, right? At equilibrium, what happens? At equilibrium, this is the Gibbs free energy at standard condition. Del G naught it is at standard condition, right? At equilibrium, this del G is equals to 0. It's not del G naught, it's this one. Del G is equals to 0 and Q becomes Kc. When you substitute these two here, so we'll get del G naught is equals to minus 2.303 RT log Kc, right? RT log Kc. Okay, so this is again one of the relation we have, which is again important. On the basis of this also, you'll see some questions. Okay, now the next thing we have here, that is Lee Chatlier's principle. We'll discuss that with the questions. Okay, we'll see a few questions which has been asked. Okay, but before that, one important discussion we'll do in Lee Chatlier's principle, which is related to the physical equilibrium. Okay, physical equilibrium we'll discuss. So you all must copy it. I don't know whether you have done this or not in the last year. You have done it or not, I do not know, but you uh, do this, right? Okay, this one, write down Lee Chatlier's principle and heading you put physical equilibrium. See, Shweta, if del H less than 0, the see, we are taking a condition. It is not about when exothermic or endothermic reaction is there. So what will be the final temperature? What I am telling you, that if the reaction is exothermic, then del H will be less than 0. Now, for this reaction, which is an exothermic reaction, if we increase the temperature, then what happens? And then if you decrease the temperature, then what happens? Okay, so final temperature, it's fine. Like when the heat is going out, obviously the final temperature will decrease. But the same reaction which is of exothermic in nature, we can have that reaction, or we can like the reaction may be there at different temperature. We can give it higher temperature, we can do that particular reactions at lower temperature. So what happens when the same reaction is at higher temperature and lower temperature? That is the question. Okay. So the condition we are taking, that at this endothermic reaction, when temperature increases, what happens? When temperature decreases, what happens? So exothermic, endothermic, we have two different cases. Total 4 cases we have. Okay, that is the condition we are taking. Now you write down application of Lee Chatlier's principle. This is important. Okay, so you just try to understand application of Lee Chatlier's principle. You know what is Lee Chatlier's principle? What is Lee Chatlier's principle? Do you know? See, Lee Chatlier's principle is what? When an equilibrium is subjected to any change, right? When you are changing the equilibrium state, or if you are disturbing the equilibrium state in any process, equilibrium in any process or reactions, like if you are changing the concentration, if you are changing the temperature or pressure, right? So any change in all these terms, or if you are adding catalyst, right? And all these things depends on the stoichiometry of the reactions also, right? Suppose you have any reactions, and suppose if you are changing the concentration of product, if you are changing the concentration of reactant, sorry, concentration of reactant, or if you are changing the pressure, or if you are changing the temperature, or if you are adding the catalyst, okay, any change in this kind of will eventually disturb the equilibrium of the reaction. Suppose the catalyst is positive, right? So that will increase the rate of the reaction. So equilibrium will attain faster in that case. Okay. If you are increasing the concentration of reactant, right? So again, it tries to maintain the equilibrium. the reaction starts going into the forward direction, right? So that is what the Lee Chatelier's principle we have. Any change in concentration, temperature, or pressure, or if you disturb the equilibrium, the reaction goes in that direction, which will minimize the change that you have produced in the reaction. Okay, so yeah, it's under physical equilibrium. I'm just giving you a brief idea of Lee Chatelier's principle. Then I'll tell you physical equilibrium. Have you done this in the last year? Physical equilibrium, like what is the effect in boiling point of water when we increase the temperature and all? Have you done this physical equilibrium? Okay, fine. Yeah. Okay. So tell me one thing then. Suppose I am taking application of Lee Chatelier's principle. I am taking what? I am taking boiling of water. Boiling of water. So H2O liquid, H2O liquid will convert into H2O gas. Correct? Now you tell me one thing. If we increase the pressure, right? If we increase the pressure, then what happened on the boiling point of water? If we increase the pressure, then what happens on the boiling point of water? Will it increase or decrease? If if pressure increases, then boiling point increases or decreases? Boiling point increases. Okay. So so I think most of you are saying increases, but it is a mixed response. 3, 4 response are there, decreases. See, actually you can understand this by two methods. Since we have done solution also, and I have discussed boiling point, why, if you remember, I have discussed why the boiling point of water is 100 degrees Celsius. Yeah, I have discussed this why the boiling point of water is 100 degrees Celsius, because at 100 degrees Celsius only the vapor pressure of water is equals to the atmospheric pressure. And when we increase the atmospheric pressure, then water requires more heat to to reach that particular pressure of atmosphere, to so that its vapor pressure increases, and hence we say that the boiling point of water increases. Okay, so boiling point will obviously increase since we are increasing the pressure. I have taken the example why cooking is difficult at higher altitude, because the pressure is less over there. Okay, but that is one way through which you can understand. We have one more like way to understand, right? The point is what? H2O liquid to gas conversion is there, right? Liquid to gas conversion is there. Now when you increase the pressure, right, when you increase the pressure, then to minimize this, because according to Lee Chatelier's principle, whatever change we produce, the reaction will move in such direction so that that particular change is minimized, right? If pressure increases, then how do we minimize this? By decreasing the volume. According to Lee Chatler's principle, when pressure increases, to minimize this, we have to decrease the volume, means volume decreases, right? It means what? When you increase the pressure, the reaction starts moving into that direction where the volume is less, according to Lee Chatler's principle, right? Now you tell me one thing, whether in which direction the volume is less, whether backward direction or forward direction. In which direction the volume is less, backward or forward? Backward direction the volume is less. Right, correct. No, it's not forward, Pratik, because you see in forward direction we have gas, right? So gaseous molecule always occupy more volume than liquid and then solid also, right? So gaseous molecule occupy more volume, so obviously this side, liquid side, we have less volume than the gaseous side, correct? So here you see the liquid molecule will have less volume, and this side we have what? Large volume or more volume, right? So when we increase the pressure, the reaction goes in that direction where the volume is less. So obviously under this condition the reaction starts moving into backward direction, right? Now you see one thing, like you just listen to me carefully, right? This one, at the same condition, liquid is not converting into gas, but gas is converting into liquid. It means the vaporization or evaporation or boiling of water is difficult over here. If it is easier, then obviously liquid starts converting into gas. But it is not the thing over here. The thing is what? The gas is converting into liquid. It means the boiling is difficult. Boiling is difficult. It means what? That the boiling point has been increased. And that's why we say as pressure increases, boiling point increases. Is it clear? Is it clear? Tell me. Right. Now, second case we take, that is melting of ice. Melting of ice. Okay. So melting of ice means what? H2O, solid, is converting into H2O, liquid. Okay. In this, you tell me, as pressure increases, then what happens? More water will form or more ice will form. In which direction the reaction goes as pressure increases? As pressure increases, then what happens? Whether the reaction goes into forward direction or backward direction. Pressure increases, freezing point increases. Yeah, that's correct. Freezing point increases means forward. Yeah, correct. You see, you can understand this is the special case because usually solid substance has high density than the liquid substance, right? Solid substance has high density or more density than the liquid substance, but it is a special case of ice because ice is a solid but it has low density, right? Ice has low density in comparison to liquid. This liquid has high density. Okay, now if it is low density, it means what? Low density means what? High volume. Okay, if density is low, it means the volume is high. High volume, high density means low volume. I'm explaining you this thing in the same way. Like here, we have compared with volume. You see, less volume, large volume, then pressure increases. The reaction should go in towards the direction where the volume is less. The same thing I'm trying to explain over here. Yeah, volume of ice is greater than volume of water. So high volume. Now you see again the pressure we are increasing. So reaction should go what? In the direction where the volume is low. So this will go towards what? Forward direction. So at the same in the under this condition, the reaction moves in forward direction. Forward direction, right? Freezing point increases, right? So in this case, when the pressure is increasing, forward direction the reaction goes and more water forms. More water forms. This is the special case of ice we have, correct? But you see, if you take any other substance, right? Suppose the third one we are taking, melting of other substance, other solid substance. In case of ice, the thing is different because ice has low density than water, right? But if you have any other substance, solid substance, suppose we have XS, and if it is going into liquid, that is XL, right? So in this, what happens, since this XS solid has more density than water, correct, than the liquid, okay, it has high density, and this liquid has low density. But in case of ice, this thing was reversed here, right? High density means what? Low volume. Low density means high volume. Now in this, if we increase the pressure, reaction goes towards low volume. As pressure increases, then backward reaction, backward reaction, and then freezing point, freezing point decreases, more solid forms. Solid forms. Correct? Yeah, that's what. That's what, Sweta. Correct. Freezing point decreases. So freezing point of no, it's not about water, Shweta. This is for any other substance. Here, what we say, as the reaction goes towards forward direction, so freezing point will increase over here because the formation of ice is difficult. More water is forming. If the freezing point decreases under the same condition, then more amount of ice should be there. Is it clear? Okay. One last uh, application of this. We'll see some questions after this. Fourth one, diamond and graphite. Diamond and graphite. Okay. See, diamond has high density. Diamond has high density than graphite. The density of diamond is high, and this has low density. High density means low volume. Low density means high volume, right? As pressure increases, as pressure increases, the reaction goes backward and more diamond forms in this case, right? As pressure increases, yeah, right, Shweta. It should be opposite. So as pressure increases, the same thing, I'm not writing down everything here, more diamond forms. Okay, one more information I'm giving you here. This process is an endothermic process, right? This is an endothermic process. You should keep this in mind. So del H should be greater than 0. Now in endothermic process, as temperature increases, what will be the K value? K will increase or decrease? Tell me. As temperature increases, then what happens? K increases, right? So when K increases, then what happens? The reaction goes in forward direction. K will increase. Mine Mohan, check your calculation. As endothermic reaction, when temperature increases, log K2 by K1 will be positive in that case. Log K2 by K1 is positive. So yeah, so it will increase. So when K increases, as temperature increases, K increases, and when K increases, the reaction starts going in the forward direction. So more graphite will form. More graphite forms, right? If I ask you, as temperature decreases, when temperature decreases, then K also decreases. Then more diamond will form. Accordingly, you have to answer this, right? Yeah. Now you see some questions on this. Okay. The question is, we have to find out total pressure. Okay. Calculate the total pressure. Okay. I'll write down the question. Calculate the total pressure. Calculate PT, total pressure. developed in a vessel containing a mixture containing a mixture contains 3 parts of H2, 3 parts of H2 and 1 part of N2 and 1 part of N2. To give a mixture, to give a mixture containing 10% ammonia, containing 10% ammonia at equilibrium, at 450 degrees Celsius. This percentage is given on the mole basis, mole percentage it is. Okay. At this temperature, the Kp is given. It is the experimental value, so it should be given. It is 1.6 into 10 to the power minus 4 atm. Try this one. Done. 0.04 atmospheric. Total pressure, Vaishnavi. We have to find out total pressure. It's not right. 1.4. What are you doing? Okay, you see. Okay, the reaction is what? It is given that 3 parts of H2, right? So we'll write N2 plus 3H2, and this gives 2NH3, and Kp value is given for this one. Okay, now you see, since it is given in the question 3 parts of it and 1 parts of nitrogen, so we have to take this mole ratio in 1 is to 3 only. That ratio you have to maintain. You cannot assume 1 mole and 1 mole over here. Okay, that is one thing. So what I'll do here, I'll just take 1 mole of this N2 and 3 mole of H2 here. 1 is to 3 ratio. I take the simplest ratio. But whatever you take, the ratio must be 1 is to 3. 1, 3, and this is 0 initially. Now we'll write what? 1 minus x, 3 minus 3x, right? Because 1 mole reacts with 3, so x reacts with 3x. 3 minus 3x, and this is 2x. 7.13 is also wrong. Okay. Now you see, what is given next? Mixture containing 10% ammonia at equilibrium. Now, suppose we have equilibrium over here. So, what is the amount of ammonia present? That will be what? Amount of ammonia is what? 2x divided by, it is the amount of ammonia, moles of x, moles of ammonia, divided by total number of moles. Total number of moles will be what? This plus this plus this. That will be 3 plus 1, 4. 3 plus 1 minus 4x plus 2x. So I think 4 minus 2x we have total number of moles. 4 minus 2x is the total number of moles. Correct? This into 100 is equals to 10. Is it clear? It is given in the question. The percentage composition of ammonia. Since it is given as mole percent here, you see, mole percentage is given, so I have taken mole over here. 0.43. Shweta, that is also wrong. Fine, no, this one is correct. Now from this you can find out x, right? And when you solve this, you'll get x is equals to. So okay, so I'll write down. Suppose this is 2 and 2 will get cancelled. So x divided by 2 minus x is equals to 0.1. So that will be x is equals to 0.2 minus 0.1 into x. So that will be x is equals to 2 by 11 we are getting. This is the value of x, 2 by 11. Correct. 2 by 11. Now it's simple now. Kp you have. So Kp, how do you have to find out? Mixture containing this. How we have to find out total pressure, no? So Kp is what? It is the partial pressure of NH3, right? Partial pressure of NH3 square. Yes, because 2NH3 we have, divided by partial pressure of H2 cube into partial pressure of N2. Partial pressure of NH3 will be what? It is 2x divided by 4 minus 2x into total pressure. I'll write down separately this one. It's better to calculate PNH3 separately and then we'll substitute over there. Okay, so 2x is what? 2x is 4 by 11 divided by 4 minus 4 by 11. So you'll get 11 into 4 is 44 minus 4 is 40. So it is 1 by 10, 0.1. Right? Now, pressure of N2. I forgot to write here total pressure, PT. Suppose P is the total pressure, so 0.1 into P. Pressure of N2 will be what? 1 minus 2 by 11. So 1 minus 2 by 11 is 9 by 11 in the numerator, divided by again 4 minus 4 by 11. So 40 again. So 9 by 40 into P. Here also will write P. Right? This is one, this is second. And the pressure of H2 will be 3 into 1 minus x. 1 minus x is 9 by 11. So it is 27 by 11 divided by again 40 by 11 into P. That will be 27 by 40 into P. Okay, and then we have to substitute this here and then you have to solve. Little bit of calculation, I know it is there. This question was asked in BitSat. Okay, the answer is 30 atm. Yeah, 30.03 is the correct one. Okay, so total pressure we are getting here 30.03 or 30 atmospheric, it's right. So little bit of calculation you have. What I'll suggest, if this kind of question you got this kind of calculation, you should leave this kind of question for the last. If in the last you have 10-15 minutes left, then you can solve this calculation and then you'll get the answer. Okay, so 30 atmospheric is the right answer. Okay, another question you see. Okay, you see this one reaction is given. I'll not give you much questions in which the calculations are involved. Okay, conceptual, I want you to understand the concept. You see this reaction is given plus y gas and this gives x3 y gas. This is the reaction it is given. The question is equilibrium is affected by. Okay, the question says equilibrium is affected by. First option we have temperature and pressure. Second one, only temperature. Only pressure. Temperature, pressure, and catalyst. Think on it and then answer. Answer. Why not D? Sanjana, Vrishali, Ritvik, why not D? Answer. Changes both equally. Catalyst. The reaction proceeds faster, that's all. Because alter forward and backward reaction equally. It only increases the rate of reaction. Yeah, correct, correct. See, actually, what happens? Catalyst won't affect the equilibrium condition. Equilibrium thing will not change by catalyst. It only helps the reaction to go with a faster rate if the catalyst is a positive catalyst, right? If it is a positive catalyst, the equilibrium will attain faster, right? It won't change the equilibrium condition. Means what? Suppose you have a reactions without any catalyst, right? So you try to understand like this. Suppose if I take one graph here. Okay, now suppose like I have told you, the graph goes like this. Okay, for any reaction it goes like this depending on the reaction is endothermic or exothermic, right? If it is exothermic, the product will have the lower energy than the reactant. This is the energy, and this is the progress of reaction, x-axis of reaction. Okay, now what happens, this is, suppose this is the reaction we have without catalyst, without catalyst. Now if I use one catalyst into this, and if the catalyst is, suppose, the positive catalyst, if you have, then that positive catalyst, what happens, will decrease the activation energy, and the reaction proceeds like this. So this is the decrease in activation energy. Initially the activation energy will be here, is here, somewhere here. Now the activation energy decreases. So you see the final and initial and final position are same. But since this blue one, this yellow one is with catalyst. So what it does, it decreases the activation energy and helps the reaction to attain equilibrium with a faster rate. That is what the purpose of catalyst we have if it is positive. Suppose the catalyst is negative catalyst, that will increase the activation energy like this, and then the reaction proceeds, but again the final position will be same. Okay, so that won't change the initial and final position. So equilibrium does not affected by does not affect by the catalyst. It only changes the rate of forward and backward reaction. Okay, that is only the thing we have. Now as this pressure thing is concerned, I'll just discuss one thing here, and that's why I haven't discussed this thing separately in Lee Chatlier's principle. Okay, effect of pressure, if you have to understand. Correct. So how do we first of all, I'll tell you the answer of this. The answer is A, it's correct. All reactions get affected by temperature, pressure, concentration of reactant and product. Okay, temperature, pressure will always have some effect on the equilibrium, right? Because most of the reactions are what? It is exothermic or endothermic. Whatever it is, temperature will have one effect. If it is not mentioned that there is no del H will be zero, then maybe one thing it is there. But since it is not mentioned, so temperature will also have will definitely have one effect. Okay. Now pressure, like how do you assume? Suppose I'll just explain you one thing over here, that is effect of pressure. Okay. Suppose we have A gas plus B gas. I'm taking any general reaction, and that is what we have here, right? This gives you C gas and D gas. Okay. Now in this you see, since del Ng is zero over here, del Ng is zero, right? So Kp if I write for this reaction, Kp if I write, and this is the type of reaction where del Ng is equals to 0, because number of product 1 plus 1 2 minus 1 plus 1 2, it is 0, correct? So Kp is equals to what? The partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B, and that will be mole fraction of C into mole fraction of D divided by mole fraction of A into mole fraction of B into P square. Here also we get P square. Here also we get this. P is what? It is a total pressure. P is the total pressure, correct? So this P square and P square gets cancelled over here, right? Is it clear? So basically what happens, if the reaction is of this type, when del Ng is equals to 0, you see if Kp is independent of pressure over here, right? This Kp is independent of pressure over here. When it is independent of pressure, so pressure won't have any effect on equilibrium. Won't have any effect at equilibrium. Okay, so if the reaction is of this type where del Ng is equals to 0, suppose the same question if I ask you for this reaction, then the answer will be only B, only T, that is B option. Okay, since del Ng is equals to 0, so in the expression of Kp, there's no pressure term involved, so pressure won't have any effect in this reaction, and the reaction is only affected by the temperature. Answer will be B for this particular reaction. Understood this? Now, if I write down this reaction where del Ng greater than 0, suppose, and that will be, suppose this A gas gives B gas and C gas. Suppose this is the reaction we have. Obviously, for this reaction, del Ng. So, if it was liquid state, the product, the reactant state, gaseous state, won't the answer change? We won't consider liquid state here, because uh, for liquid molecule and reactant, we don't consider partial pressure, no. So we'll not get any liquid state over there. If it is there, you just have to ignore them. Okay, you have to ignore them. Now suppose if del Ng is greater than 0, so I'm just, in short, I'm writing down the Kp expression because I hope you have got it already. So Kp expression will be the mole fraction of B into mole fraction of C divided by the mole fraction of A into total pressure will be there, because in the numerator we have P square and here we have P. Is it clear? This one, the second one, is it clear? Tell me. Right. So this kind of reaction where del Ng greater than 0 or less than 0 will have some effect on equilibrium. Right. So that's why you see the reaction here it is given. It is del Ng is what in this case? Sorry. Del Ng is less than 0, which is the next case we have that we'll see just now only. Like I told you in the beginning, that we'll try to understand the concept with the help of questions that has been asked. And let me tell you one more thing. This question was again asked in JE. Okay, so we are only discussing good questions now. Okay, so you see, now you tell me one thing. Obviously, that you have understood this, that pressure will have some effect because Kp terms involve, Kp expression involves pressure terms over here. Correct? Now, if I ask you this thing, as pressure increases here, then in which direction the reaction proceeds? Tell me. As pressure increases, in which direction reaction proceeds? Forward or backward? Backward, backward. Okay. So backward, right? Why it is backward? Because you see, when pressure increases, this Kp is independent of pressure, right? It depends only on temperature. Oh, sorry. Right. For equilibrium to maintain, this Kp wants to be constant, right? The tendency for Kp is to be constant, right? So when this pressure is increasing, to maintain this ratio over here, Xa will also have to increase. Correct? Then whatever amount by this pressure is increasing, if Xa will also increase, then this ratio will be maintained and Kp will not change. The point is what? Kp tries to maintain this value, its value, right? Since it always have the tendency to maintain the equilibrium. So Kp does not have the tendency to change, right? To get itself change, right? So when you are increasing the pressure, Xa has to increase so that this ratio will maintain. And when this Xa will increase, so what I should write here? As P increases, according to Lee-Chatlier's principle, Xa should increase. When Xa increase, it is only possible when the reaction goes in backward direction. Backward direction. So as pressure increases, backward direction, backward reaction favorable. Again, we can say what? As pressure decreases, then reverse of this will be true, and that will be what? Forward. Forward reaction favorable, right? Yeah. So one more case, last one I'll just, which is nothing but this del Ng less than 0. For this reaction, only suppose if I write down the Kp expression, that will be what? Mole fraction of this product x3y divided by mole fraction of x cube into mole fraction of y divided by p cube into p4 and p over here we have p cube, right? So basically this expression is not important. The only thing you have to keep in mind that the Kp expression involves pressure term, so obviously the equilibrium affected by the pressure here, right? So answer will be temperature and pressure, option A, right? So like this you can easily write down the expression of Kp, and you can understand whether it is independent of pressure or not. One more thing, you see, this question is also has also been asked in JE. This one, for one reaction, and the reaction is this. Next question I'm giving you. Reaction is A2 plus B2 gives 2AB. 2AB. And for this, the equilibrium constant is given, which is K, right? What is the equilibrium constant for the reaction AB gives half A2 plus half B2? Tell me the equilibrium constant for the second reaction. One by root k. So all of you are getting the same. Um, yeah, I think it's correct. Okay. So by whatever number we are multiplying, that will come onto the power of k, right? So basically, like, so when we reverse this, for this it becomes k 1 by k, and since we are multiplying this equation by half, so 1 by k to the power half. Whatever number with which we multiply the reaction, that number comes onto the power of it, this k. Why 1 by k? Because we have reversed this reaction. Okay. Next question, you see. Um, Same kind of question, you see. This question was also asked, is also asked in JE. This was asked in JE. Okay. This is also asked in JE. And the question is H2 gas plus I2 gas gives 2HI, 2HI gas. Then the question is Kp changes with. Kp changes with. First option, total pressure, Pt. Second option, catalyst. Third option, amount of H2 and I2. H2 and I2. And the last one is temperature. It's D. Vaishnavi is saying it's D. This is also asked in JE. Yeah, everyone is saying, so it's correct. You see, actually, for this reaction, you see del Ng is what? Del Ng is 0. So obviously it is independent of pressure. Just now we have discussed. Okay. So this is not possible. Catalyst, again we have discussed, not possible. Amount of H2 and I2 won't affect Kp because accordingly this ratio of product also will change. Also not possible. Only temperature it is possible. Right? Simple reaction it is. Simple one it is. Now you see one question that they have asked in this. Where's that? Hmm. Okay. See this one. The degree of dissociation. Question is this. The degree of dissociation is zero point 0.4. I'm giving you in short data only. I'm giving you. Alpha is given zero point 0.4 at 400 Kelvin. At 400 Kelvin and 1 atm pressure. And 1 atm pressure for the gaseous reaction, and the reaction is this: PCl5 converts into PCl3 plus Cl2. All these are gaseous reaction. All gases behaves ideally. Calculate the density of equilibrium mixture. You have to find out density of equilibrium mixture at the same temperature and pressure. The relative atomic mass of phosphorus is given. It is 31, and for chlorine it is 35.5. You have to find out the density of the mixture. Relative atomic mass is given. Gases are behaving as an ideal gas. Why not C? Okay, Ritvik. See, why C is not possible? Because suppose if you, the thing is, Kp changes with, obviously Kp will have certain value, right, at equilibrium, because every reactant and product will have certain number of moles at equilibrium, and according to that will have the partial pressure. Okay, so when the Kp will change, when the number of moles of these reactants and product will change, correct? So what we are doing, we are amount of, suppose if you take the higher amount of H2 and I2, according to that only the amount of Hi will also form. Understood? So this Kp, since temperature we are not changing, so Kp value will be maintained accordingly. If you take high amount of H2 and I2, more amount of H2 and I2, more amount of HI will also form, so that the ratio will be maintained. Ratio of partial pressure will be maintained. Understood? This question is a subjective question. There is no option in it. Okay, the question that I've given you, subjective question asked in JE mains, 1980s, 84 or something. 1998. JE main 98. 10.64. The density of the mixture. 10.64 you are getting. How it is 10.64? It's wrong. It is not tough. Check your calculation. 5.97. It's wrong. It's not 5.97. 4.53 is right. 4.53 is close enough. Is right. Kushal. 4.53 is correct. You see, actually, this is like, it looked like a bit weird because chemical equilibrium is a chapter and the question is we have to find out density. Okay, but it is not tough at all, because you see, density, we know density is what, mass by volume, right? And in the question I've told you that the all gases follows ideal behavior, right? 4.53 is correct, Purvik. Okay, ideal behavior. So density, if you have to find out, it is what, it is mass by volume. How do we find out? So mass, is the mass is given in the question? Tell me. Mass is given in the question or not? See, PCl5 molecular mass we can find out. That will be what? 31 plus 5 into 35.5. Right? and this will come somewhere around, it is 177.5, 177 plus 31, it is 208.5. This is the mass, total mass, correct? And reaction starts from this PCl5, whose total mass is 208.5 gram. And since it is the case of equilibrium, so obviously the reaction takes place in a closed container. Like I told you, whenever the equilibrium case is there, the container must be closed, right? Open container, equilibrium won't establish, right? And when the container is closed, so the mass will be conserved. Mass will not change, total mass will not change. It is a different case that some of the PCl5 has been converted into PCl3 and Cl2, but total mass at any point of time, it will be 208.5 gram. Correct? So mass basically we have, right? Mass is 208.5. This is already given in the question. Only thing is what? Volume we have to find out. Okay. Now how do we find out volume? For that, the second data is given in the question, which says that the gases behaves ideally, right? And for that, we have to apply PV is equals to nRT, right? So you see the pressure is given 1 atmospheric, temperature is given 400 Kelvin, R value we have already, R value will take 0.0821, right? So volume we can find out from here. So volume is equals to what? nRT by nRT by P. Everything is given, only N is not given, that is number of moles, right? N is not given. Now, how do we find out N? N is what? N is the total number of moles we have basically, right? Total number of moles. So for that, we'll apply the concept of chemical equilibrium. For this reaction, if I write PCl5 converts into PCl3 plus Cl2. If it is 1 initially, 0 and 0, right? So it is 1 minus alpha. This is alpha. This is alpha, right? PM is equals to DRT. No, it's not wrong. You'll get the same thing, Shweta. You'll get the same thing. That is what I am doing. D is what is D? PM by RT, right? PM by RT, and that is what I am doing. I am taking volume. What is the answer you are getting with this? PM is equals to DRT. Check once. Now in this you see 1 minus alpha, alpha and alpha. Total number of moles at equilibrium will be 1 plus alpha. Alpha value is given 1.4. That will be 1.4. So N value will be 1.4. Okay, I'll check it. Wait. N value will be 1.4. This N value you will substitute here. 1.4. R is 0.0821 into 300. Sorry, 400 to 400 divided by 1. Right? This gives you volume. This volume you substitute here, you'll get the answer. Okay, one thing, Shweta, you cannot use this formula here. because this is applicable when we have only one gas present. Understood? Pm is equals to dRT, applicable when we have only one gas. For mixture of gas, we cannot use that. Understood my point? For mixture of gas, you have to calculate the number of moles. Why you are getting different answer there? Because of number of moles. Because at equilibrium, we have PCl3 also present and Cl2 also present, which has different number of moles. So Pm is equals to dRT. Everyone concentrate on this. Pm is equals to dRT. If you remember there, we can use this formula only we have only one gas present. If we have mixture of gas, we cannot use that, because which density we are calculating over here? Density of the mixture, no? Here we have in this formula, it is the density of the gas, one gas. Okay? So answer you will get is 4.5354. Understood? Done? 4.5354 will be the answer. Just you substitute this volume over here, you'll get the answer. The important thing is what you have to keep this in mind, that the molecular formula of PCl5 you know already. Calculate the total mass, and that mass will not change since this is a case of equilibrium. Okay? Okay, next one you see. You see this reaction is given A plus 2B gives C plus some heat releases in this process. The question is, forward reaction is favored by. Forward reaction is favored by option A, low pressure and high temperature. B, low pressure and low temperature. Low temperature. High pressure, low temperature. And the last we have high pressure and high temperature. After this, one more question, a small one I'm giving you. You have to find out the active mass. Active mass of 64 gram of HI in 2-liter flask. Option C. Yeah, option C is correct. Low temperature and high pressure. You see, the reaction is what? The reaction is exothermic, because heat is releasing. Heat is releasing, so reaction is exothermic. Del H is what? Del H is less than 0. Okay. forward reaction we have to go, means K must increase into this. According to the question, K must increase. So log K2 by K1 is equals to minus del H by 2.303 R 1 by T2 minus 1 by T1. So this is negative del H, negative, negative, positive. This has to be positive for forward reaction, right? Because K2 must be greater than K1. That is the condition we have to satisfy. This must be greater than 0, right? So 1 by T2 greater than 1 by T1. So T2 is less than T1. Means the temperature should decrease. So low temperature favored. So either this one or this one. Okay? Either this one or this one. Now high pressure, since it is the case of what? Del Ng. Del Ng less than 0. Just now I have discussed this is favored by high pressure only. So option C is correct into this. Right? Okay. Yeah, 0.25 is also correct. 5 minutes more, Kushal. I'll give you a break. Okay. 0.25 is also correct. Active mass is nothing but concentration. Active mass is nothing but concentration. So, number of mole per liter. One last question, then I'll give you a break. Okay, one more question. One more question. We'll see. Then we'll take a break. Okay. Okay. You see this one. After this, you'll get a break. One more question we'll solve. The vapor density of a mixture consisting NO2 and N2O4. We have a mixture of NO2 and N2O4. For this mixture, the vapor density is given, and vapor density is equals to 38.3. 38.3 at 275 Kelvin. At 275 Kelvin. We have to find out the number of moles of NO2 present in the mixture. Moles of NO2 is equals to what? Vapor density is the only thing which is given. Number of moles of NO2. What is the answer? Tell me the answer. 1 by 2. 1 by 2 is not correct, Purvik. Okay, you see, I'm doing this. First of all, you see, uh, vapor density is given, right? And what would be the reaction in this? The reaction we can write like this: N2O4 converts into NO2, right? And when you balance this reaction, we should write here 2. 0.5 is not correct, Ritvik. Okay, this is the reaction we have. Okay, so now when it is 1 mole, it is 0. So 1 minus alpha gives you 2 alpha. And what we have to find out? Moles of NO2. Means we have to find out what is 2 alpha. Correct? So if you know alpha, you can find out 2 alpha also. So basically, we have to find out what is the degree of dissociation. Right? And since vapor density is mentioned in the question, so you don't have to do anything, but you have to use only this formula: d minus d divided by n minus 1 into d. Okay, what is capital D? It is a vapor density before dissociation, right? What is this given? This is nothing but the small d, vapor density of the mixture. Small d is the vapor density of the mixture. Capital D is the vapor density before dissociation. So when there is no dissociation, there is only N2O4 present, right? Okay, so its vapor density you have to find out. So that will be what? Molar mass of this is what? 14 into 2 plus 16 into 4 divided by 2. This is nothing but the capital D, vapor density before dissociation, right? Why by 2? Because we know the molar mass is equals to what? 2 into vapor density. So vapor density we are calculating, so molar mass by 2. 16 into 4 is 64. 64 plus 28 is 92, by 2 is 46. Okay, now you have everything. Substitute here, you'll get D. D is 46 minus small d is 38.3 divided by n. I told you this n is the number of product molecules. We don't have to do anything with this, right? How many product molecules we have? 2. N is 2. So 2 minus 1 into 38.3. Right. So when you solve this, you'll get 0.77, and they had divided by 38.3. So that will be approximately, if I take point 0.2, 38 into 2 is 76, right? So point 0.2 something you'll get. Point 0.2 approximately I am taking. Okay. And you have to find out 2 alpha. So 2 into point 0.2, that will be point 0.4. This is what you have done, Purvik, Ritvik, Pratik. This is what you have done. If you take 0.25 as alpha here, then the answer will be 0.5. Oh, if you have done like this, it is correct. Otherwise, it's wrong. Okay. So answer will be zero point 0.4. Okay, correct, Purvik. If you have done the same thing, then it's correct. Okay. So keep the formula in mind. Whenever vapor density is mentioned in equilibrium question, alpha you can calculate with this formula. I told you in the beginning also, this formula is useful for alpha. Okay, so it's already 7:10. By what time will start? Okay. So we'll take a break of 10 minutes. We'll start at 7:20. Okay, 7:25 will start then. Okay, so don't be late. 7:25 will start. Okay.
Hello? Okay. Give me a class that will just break the 20% 8:30. Okay. ठीक है मैं फोन करता हूँ
Okay, so we'll see two more questions on this, and then we'll start ionic equilibrium. Okay. See, I am not discussing about these kind of questions, which is related to this Kp-Kc relation. Kp is equals to Kc RT to the power del n. Okay, I'm not discussing these questions because these are very, very basic. Okay, on the basis of reactions, del ng you can calculate, and you can easily find out whether Kp is greater than Kc or less than Kc or equal to Kc. This kind of question also they ask. Okay, this particular formula I'm not discussing now. Okay, you can do this question on your own. Two more questions we'll discuss, and then we'll start ionic equilibrium. Okay, so the next question you see, um, at 250 degrees Celsius, at 250 degrees Celsius and 1 atmospheric pressure, and 1 atmospheric pressure, the vapor density of PCl5, vapor density of PCl5 is given, and that is 57.9. The first thing we have to calculate in this is Kp, and the second thing is percentage dissociation, percentage dissociation, dissociation when the pressure is doubled. When we increase the pressure, then what is the percentage dissociation? We have to find out. Solve this one. Done. Okay, see, I'll just give you some hint over here. First of all, dissociation of PCl5. The first step is to write down the reaction. All are gaseous form. So PCl5 gives what? PCl3 plus Cl2. Right? Nothing is given. We assume 1, 0, 0. If alpha is the degree of dissociation, then we have it as 1 minus alpha, alpha and alpha. 79%. Kp is 137 point. What is 79%, Ritvik? Oh, second one. Second one is 79%. What about the first one? It's huge. Purvik, 137.4 is not correct. See, you first of all you trying to no understand the roadmap of the question. What is the question? What is the you know data or value we required? 133. No, it's not correct. It's not correct. You see here. First of all, obviously dissociation of PCl5 we have. So PCl5 dissociates like this. Now Kp is what? Since Kp you have to find out. So expression for Kp will be what? It is the partial pressure of PCl3 into partial pressure of Cl2 divided by partial pressure of PCl5. Okay, total pressure we know, and that is 1 atmospheric. Okay, so partial pressure of PCl3 is what? Mole fraction into total pressure. So mole fraction of PCl3 is what? Alpha is the number of moles of PCl3 divided by total number of moles, this plus this, which is 1 plus alpha into 1 total pressure. Similarly, if I write for Cl2, that is also the same thing, right? Because alpha is same over here. So I'll just write down the square of it. This divided by 1 minus alpha divided by 1 plus alpha into 1, right? And when you solve this, you will get what? Alpha square divided by 1 plus alpha into 1 minus alpha square. Okay, now the point here is what? You have to find out alpha. If you know alpha, you can find out Kp, and that is what the first question. And like I told you in the last question also, vapor density is given. So you have to use what formula to find out alpha? You have to use this one, vapor density formula. So alpha is equals to d minus d divided by n minus 1 into d, right? D is given. This is nothing but d, small d of the mixture. Vapor density, that is capital D of the PCl5 is what before dissociation? It is for phosphorus 31. 5 into 35.5 divided by 2. That gives you that gives you 208. This is 50 50 32. Okay, huh. So we'll get 104.5 by 2. 208.1 gives you 108 104.5 or 25 probably will get here. 25. Okay. Now you see everything is given. Just you substitute here 104.25 minus 57.9 divided by 2 minus 1, and value is 2 because the number of product we have to check, PCl3 and Cl2, into 57.9, and when you solve this you'll get 0.80, 80% alpha degree of dissociation. 2 by 3, so 2 by 3 alpha is 0.891, correct? 1.77 kp, 1.77 kp is correct. Mrs. Straw got the answer. 1.77 is correct. Okay, so alpha you have, just you substitute alpha here, you'll get the answer zero point 0.8 square divided by 1 minus zero point 0.8 square, and the answer you will get 1.78 or 77 approximately. Okay, so Kp, the first portion we have done. Now percentage dissociation when the pressure is doubled. Excuse me. So basically here, when the pressure is doubled, so this P becomes what? 2 atmospheric. Just we have to substitute here. So here we have 2 and 2. Kp will be same. Kp will not change. So expression I'll write down here. 1.78 for the second portion. 1.78 is Kp is equals to alpha square, alpha by 1 plus alpha into 2 whole square divided by 1 minus alpha divided by 1 plus alpha into 2. This is the expression we have. Okay, and which we get on solving is 1.78 divided by alpha square divided by 1 minus alpha square into 2. Okay, and when you solve this alpha value, you'll get 68.6%, 0.688. This is the value of alpha. Okay, you can easily cross check this. You see, initially at 1 atmospheric pressure, alpha is 0.80, which is 80%. When you increase the pressure, alpha decreases. That is what possible, because for this reaction, del Ng is what? Del Ng is greater than 0, right? And that particular discussion that we have already done, in this type of reaction, as pressure increases, backward reaction favorable. Backward reaction means what? The alpha value decreases. More reactant will get. And that is what we are getting here. 80% here, and here it is 68.6%. Is it clear? Okay. Now you see one last question for this chemical equilibrium chapter. Okay. The question is a solid converts into B gas plus C. Sorry, here we have D plus D gas. B and D. Kp1 for this reaction is given, which is 1000. Another one, C solid dissociates into plus E gas. Kp2 is equals to 500. Calculate the total pressure at equilibrium. This is actually simultaneous reaction. Okay, two different reactant you see. Two different reactant giving one common product. Okay, so both reaction will attain equilibrium, and the formation of B from this reaction will also affect the equilibrium of this, the second reaction, because B is same in both reaction. Try to solve this. Better you make this as 600. Your calculation will be easier then. This Kp2 you take as 600, not 500. Anyone? What happened? Okay, you see, I am solving this. See, first of all, like I said, this is we call it as simultaneous equilibrium. Okay, in which alpha is not given, alpha is not required. Alpha is not required, Pratik. You see, I'm solving this. First of all, this is a simultaneous equilibrium. Like I said, two different reactant giving a common product. At least B is common in these two. And it's not like that two reaction is taking place in two different container. We have the same container in which the reaction is taking place. Closed container, obviously. A is also dissociating and B is also dissociating over here. Since one of the product is common in these two, so formation of B here in this reaction, that also affect the equilibrium of this and vice versa. Means both reaction, since one product is common over here, both reaction will affect the equilibrium of each other, right? If one particular reaction you remove, then we'll have some equilibrium concentration which is different than the concentration that we have. One atmospheric is not true, Ritvik. Okay. Okay, now you listen to me carefully. Right. So the point is what? Since it is solid, so this will not have any partial pressure. So let's let it be this one. Now suppose when this reaction takes place, so obviously A dissociates into B and D. So this B will have certain number of moles, which is true for D also. And according to that mole, we'll have some certain partial pressure of B and that of D also. No, it's not true, Purvik. Okay, so suppose the partial pressure of B is P1, and since 1 mole we have, so D also it is P1. Okay, now here I assume the partial pressure of B in the second reaction is suppose P2. Here I am assuming this as P2. 1 mole we have, so this is also P2. Okay, but you see, the reaction is taking place in the same container. Like I said, that both reaction affects the equilibrium of each other. So B in the reaction vessel, whether it is coming from this reaction or this reaction, both are both depends on each other. So total pressure of B will be P1 plus P2, P1 plus P2. Means the total pressure of B, if I ask you, the answer will be P1 plus P2. The amount of B that is forming from first reaction and the amount of B that is forming from second reaction, both will exert its own pressure. So total pressure of B will be P1 plus P2. Right? Now it's easy. Now you see, if I write down the expression for Kp1, what is the expression for Kp1? Constant partial pressure of the product, which is P1 into P1 plus P2, and that is equals to 1000 given in the question. Again, Kp2 is equals to P1, sorry, P2 into P1 plus P2, and that will be equals to 600. Clear? Is it clear? Yeah, it's clear now. Any doubt? See, Vishak, the pressure of B will be P1 plus P2 because P2 pressure is because of this reaction and P1 is because of this reaction. So total pressure of B is what? If I ask you in this vessel where these two reaction is taking place, what is the pressure of B? How do you differentiate that B is coming from this reaction or this reaction? B is B only, no? What is the source of the reaction? That is not the concern. The concern is the pressure of B in the reaction vessel. So P2 is the pressure developing from this reaction, P1 from this. So total pressure is P1 plus P2. And there only the reaction will attain equilibrium. Correct? So now we have two reactions, two equation we have. Correct? What is the question? Calculate total pressure at equilibrium. So at equilibrium, what all things we have? Since total pressure we have to find out, so this solid thing we don't consider. Correct? And at equilibrium, we have B, D, and E. Correct? So at equilibrium, we have only B, D, and E. A and C will not consider since these are solids. So total pressure at equilibrium, PT, will be the pressure because of B, that is P1 plus P2. The pressure because of C, that is pressure because of D, that is P1. And the pressure because of E, that is P2. So the total pressure at equilibrium will be 2 into P1 plus P2. So this is what we have to find out. This is what the question is. Understood? Now for this you see we have two reactions we have already written. You have to solve these two reactions, you will get the answer. How do we solve this? Suppose this is reaction 1, this is reaction 2. If you add these two, you can take the ratio of these two also, but that will be again a bit difficult to solve. If you take the ratio of these two, you'll get P1 by P2, right? Nothing is given. P1 and P2 is not given into this, right? So what I'll do, I'll just add these two. So when I add these two, left hand side P1 plus P2, I'll take common, right? P1 plus P2, I'll take common, and in the bracket again we have P1 plus P2, and this will be equals to what on the right hand side? 1600. So we'll have P1 plus P2 whole square. So that will be equals to 40. So 2 into P1 plus P2 will be what? 80 atmospheric. That is the total pressure at equilibrium. How do you calculate P1 and P2? Trial and error you can use P1, P2. How did you calculate this, Sweta? P1 25, P2 50. Divide the equation, you'll get P1 by P2 is equals to 10 by 6. Okay, and then you calculate P1 plus P2 and then you substitute P1 plus P2 into this. Correct, that also you can do. That is also you can do. If you divide these two equation, you will get P1 by P2 is equals to 5 by 3. Add 1 both side, you'll get P1 plus P2 divided by P2 is equals to 8 by 3. P1 plus P2 is equals to 8 by 3 into P2. Substitute here, you'll get. So P2 square into 8 by 3 is equals to 600. So when you solve this, you'll get the answer, I think. Yeah, correct. You can solve. That's not a big deal. You can solve and then you have to find out P1 plus P2 and then this. But this is the, I think, easier method. Anything, if you get in your mind, you can solve this. Okay. So understood this. This is the question of sequential equilibrium, we call it as. Two different reactants gives you the same one of the same product. Okay. Like this will write down the expression of Kp1 and Kp2. Is it clear, all of you? Okay. Now you see, we'll start this the discussion of ionic equilibrium. Okay, so we don't have time actually, right? But okay, we'll see just ionic equilibrium. We'll continue with this in the next class also. Let's see what all things we can cover today. Okay, see, ionic equilibrium basically it is a big chapter first of all, right? And it contains calculation of pH is important, and there are 8 to 10 different cases, right? And in that you have to understand, like, what formula you have to apply. Yeah, yeah, I'm continuing with it. Yeah, I'm continuing with it. Okay, so ionic equilibrium pH calculation is one of the portion we have, right? First 50% of the portion contains pH calculation only. Okay, and then we have one concept of buffer solution, and then we have some solubility product question, solubility product. Okay, so these are the basic thing we have in this chapter. So first of all, we have to understand that what is this ionic equilibrium. See, chemical equilibrium we have discussed, and we are discussing about molecules over there. When I write N2 plus 3H2 gives 2NH3, right? So these are molecules, we don't have ions present into it. You want to solve one more question, or should I continue with it? Okay, fine, I'll give you one. Tell me quickly, one like numericals you want to solve for equilibrium only, or should I start with ionic? Okay, fine. We'll do one question only on this. See, like I said, Kp is equals to KCRT to the power del n. Those problems you just go through on your own. One question I'll give you. Okay. Okay, you see this one. One reaction is given. Okay. A reaction is this only. PCl5, PCl3, and Cl2. Same reaction I am taking as. Okay. Attains equilibrium if the equilibrium concentration of PCl3 is doubled, if the equilibrium concentration of PCl3 is doubled, the concentration of Cl2 becomes, the concentration of Cl2 becomes, first option, 1 4 1 1 fourth, 1/4 of the original value, half of the original value, twice of the original value, and the last one we have unpredictable. What is the answer? It's okay. We'll start next class, Vaishnavi. 1/4, half, half. Okay, all of you are saying A, B, A, B, A, B. Actually, the answer for this question is D, unpredictable. We cannot predict it. The only thing we can understand or we can say that when you add product into it, the concentration of product you are increasing, correct? When you are adding PCl3, the concentration of product you are increasing, right? When the concentration of product you are increasing, so obviously the reaction starts going in the backward direction, starts going in the backward direction. That is the only thing we can say. What effect takes place on the concentration of Cl2, that we cannot say into this. It may be anything, right? Because when this will go this side, so some forward reaction will also be there. So what is the effect on the concentration of Cl2, that we cannot say. The only thing that we can say, according to Chatlier's principle, that the reaction will go in the backward direction. The answer will be unpredictable. Yes, We can say that the concentration of Cl2 will decrease because the reaction is going in the backward direction. Whether it is half or 1 by 4, that we cannot say. It can be any value. Understood this? No, no, no. We cannot say Saimi here like that because when the reaction starts going in the backward direction, at the same time, forward direction is also there. The reaction is going in both direction. The only thing when you increases the concentration of PCl3, the backward reaction is dominating, right? So what effect on Cl2 takes place, that is unpredictable into this. K will remain constant, obviously, because we are not changing the temperature. K will not change. To maintain K only, the reaction starts going in the backward direction. Okay. So this is it. Like no, the questions we have probably discussed all possible type of questions. The only questions that I haven't discussed, which is Kp is equals to Kcrt to the power del n, and the question related to del G, right? Del G, that is only formula based question. You have to put the value of RT and Kc over there. Then you find out del G from there. Those kind of questions you can go through on your own, right? But now since we have almost revised every possible thing in this chapter, you can solve the questions which is given in the module or any other book if you have. Correct. So next class, in the revision class, we'll start ionic equilibrium. We'll see again little bit of theory, not in so detail, and then we'll solve the questions. Okay, right? Okay, chalo, thanks a lot. We'll continue with ionic equilibrium in the next class. Okay. Okay. Bye.